Okay, so we're starting the live stream there, and I'm going to start this stream here in Feedloop. And let me try to see if we are live in Feedloop. So far, it's every time I've checked, it's worked. But I guess it's telling that I just want to test each time, just to make sure that we are indeed live. And it looks like the meeting is joined. Okay, good. And we've got some participants that are joining us, so that's great. And it's 1 minute before. Okay, we're just on time.
Okay.
So welcome, everyone. Welcome. Thanks for coming to join us. So I guess in the technical term for broadcasters is they have this green room where you're supposed to hang out backstage, I guess, before you get brought on. And so there isn't a Zoom green room, no Zoom backstage. So let's see. We've got a few attendees. People that I recognize, some are in Australia, and some are in Philadelphia, I think. So we've got a spread. Let's see. So there's Matthew Strong has just joined, and I keep seeing him whenever I'm wandering around GatherTown. These are people that I keep bumping into, so that's great. So I'll give people another minute just to join. Although I have to say, for me, when I make an error with the timing, it's always, you know, a +1 or a -1 error in the time zones usually, and so no amount of waiting is going to help us there. At least in the list of attendees, I'm seeing Matt Strong twice, so he must be doubly. I hope you're not having a technical issue there. So first of all, Hae-Won, thank you for making the time again. It's not usual to go to a conference and have to give an hour's worth of time for your Q&A, and so I appreciate that. And there's also, of course, all the extra time which is involved in preparing the videos. And my personal reflection, which I was saying to you earlier this morning, was that I find that as an author or a presenter, preparing the talk it's a fair amount of work. But after the product has been produced, the fact that this can exist over a longer period of time, I think is extremely valuable. And so, but I think it's extremely valuable, but I need someone to force me to do it. I wouldn't do it. The delta in effort is too much otherwise. And so, so I recognize all the work you put into that. And your slides were very well organized. I have to say, certain times when you dropped your image away so that it wasn't hiding the content, all of that. As someone who's been spending some days of editing videos, I saw was care that was put into that. So thank you.
Thank you very much.
So one other thing, I made this kind of joke earlier in the previous session about sort of when I watch a video in my sub area, the videos are always sped up because the robots are painfully slow, and your robots operate, at these really fast rates, so that really for us to see the detail, you actually need to slow the robots down. But there's another slightly amusing aspect that I've noticed, which is that in the legged locomotion community, you guys have got your own kind of benchmark for testing robustness, which seems to be that you have to kick the robot. No other sub area of robotics has kicking become the de facto standard test. Or I guess in the Boston Dynamics they have the hockey, the hockey stick. So that's interesting. And I see that you're recording this video, and you've got the two students, or maybe it's the postdocs. You've got a big group there who are holding the support structure, and it falls to the PI, to the professor, to be the person who's actually going to kick the robot. And I wonder what it would be like to me if I were a grad student and I'd put all this time in, and then my professor was going to kick the device. It's sort of it's sort of a realization of the metaphor of a thesis defense. So yeah, we have an anonymous attendee. Great. I don't know how many anonymous attendees we have. That's great to know that actually that's a viable option, and they're wanting to ask real questions, not just my underarm pitches to start with. I do have some other questions to follow up with, but let's go with what the attendees say. So there's a question here, which is a broad one, and it's a really good one to get started on. And the question is, what is your view of reinforcement learning for learning robot locomotion?
Oh, yeah.
You want to cut your teeth on, right?
I think this is the kind of questions that I expected it, because I got these questions recently very often. And so my tool for my research is actually optimization and model, as you can see in my video. But I'm very open to actually RL-based method as well. And I think first of all, the RL-based method is actually really good, can be really good tool for controlling regular robot, especially when you want to deal with some dynamics which cannot be modeled very easily. Something like, the impact dynamics. So if we have a unscheduled impact sequence, then I think the RL-based method can be a really good option. RL runs the control policy by trying many things, and it doesn't care like impact happens in this, in precise schedules or not. So I think in this case, I think RL-based method is a really good tool. Like for example, if you see Jaemin Hwangbo's research published in Science Robotics, I think he made the animal robot standing on from the falling, but in very diverse poses. And if you can see that the robot utilizes contact and impact with the ground. On the feet, but as well as the body as well. So if you try to use MPC for this kind of motion, you have to have a model contact with the body and ground. So, and it can be really difficult to model in MPC. So in that case, RL-based method could be a better option for control design. And as well, recent research from the Mark Otto's group, they have a RL-based controller working on very different, grounds, very different types of ground, including sand and ice, something like that. So if you use MPC to control that, then I think you have a good model of ice and sand. And then we know that it's really difficult to model that. So some cases, RL-based method is a good option. Yeah, but I don't know how to integrate the vision-based intelligence with the RL-based control. I think some researchers are doing that, but kind of end-to-end manner, including the vision. And I'm not sure, but I think the leading researcher like Boston Dynamics is not using RL-based method for their controller, and Sangbae MIT, he doesn't use RL-based control. And what we could find when using the MPC is actually it's really easy to tune the parameters for MPC, and it works really well for many robots. And I think it's very good, starting controller for legged robot. Yeah.
Yeah, so there is an RSS paper. One of the papers is about using control policies to initiate learning this year. So that that
this year, okay.
Yeah, that seems like that could be kind of a way you could start with something pretty reasonable and save on the data dependencies, and it's quite interesting. Larry Matthews yesterday was talking about some regions in his talk. There are these parts he calls drifts, and I asked, he said these are challenging, and I said, why are they challenging? And he said, we just don't have sort of comparable sand in you know, in the world, it seems terrestrially we just don't have access to that, which is interesting. So, but you know, actually, I wanted to ask a few questions because one of the things that and so I'll preface this by saying my questions are the least important questions. You guys have plenty, you know, I'm talking a lot here just to make sure that there is that we can have a conversation. But please, if anyone has a question, jump in, fire a will, and I will stop in mid tracks and take your question for sure. But you mentioned sort of in the MPC this sort of representation free approach, and when I saw that, I thought, I'm not sure that I know. Well, I don't know what that means, because when I see that, I immediately think of something sort of model free, where, you know, we're thinking of Q learning or something. So could you just tell me a little more about what that means? Just explain that to me.
Yeah, I think representative free means that, you know, in order to represent, you know, the SO3 manifold, we utilize some minimal representation like Euler angle and quaternion, something like that. And depending on which kind of representation you use, the mathematical structure and even the dynamics can be different. But this representative free means that, and more importantly, if you use Euler angles, the mathematical structure is different with respect to the pose and configuration. So representative free means that it's not totally free from any representation. You have some representation, but the representation, that representation is kind of free from, you know, configuration dependent things, something like that. So, and actually this, I mean, I don't want to open all the things, but that title is actually recommended by one of the authors of the paper, one of the reviewers of the paper. So they want to change the title to that, representative free. So yeah, anyway, so the first title we had is actually singularity free MPC, but reviewer actually recommended to change it to representative free. Yeah, anyway.
Interesting. Thank you. Yeah, there's just there are a few things like that what I went through, and I thought, gee, if I could ask in real time, this is what I would ask, and I made a note. So I just thought, since you were talking about RL, and one of the things I thought when I first saw that was made me make this connection to model free, and of course it's not, because everything you're talking about is model based. We've got another question here, which is sort of in a similar vein to one of the ones we had in the earlier session, which is, what would be a good starting point for a new researcher in robotics RL, it says in particular.
Okay, I mean, I'm not RL researcher, so I'm not a good person to answer this question. And my answer can be wrong or can be biased or something like that. But I don't know. I mean, I actually haven't studied RL very thoroughly yet, so I don't think I can answer this question very well. But I see that my student is trying to run reinforcement learning, and I mean, I don't know. I mean, they have a really good script in Python, like PPO Python script, and then they have you know, the virtual gym environment already in Python, and it looks like it's very easy to start. But if you want to gain deep understanding of the algorithm itself, and now it's the time that the mathematics going in, and then I don't know. I mean, it's a great tool, but it seems like many students doesn't have a good understanding and deep understanding of the algorithm itself, and they utilize that as just a tool. And I don't think it's a good. I don't know. I mean, but I'm not sure that should be happen in academia and university. So I think I recommend to read some seminar papers first, yeah, and some YouTube lectures, instead of just trying to use the package, Python package and tools. So yeah.
Yeah, I would say that the sort of ad hoc tinkering, where there's a lot of trying various things and very little sort of, you can certainly use those techniques to get insight, but you're not going to stumble upon insight. I think you have to, my experience is you've mostly got to go after, you've got to have a very focused view, keep your eye on the prize, and then those tools can give you answers. But yeah, no, I think that's a very good answer. You know, one thing that actually, one thing I wanted to ask you about was about the models that you use, which are where you showed in one of the cases you were really showing the predictions of the contact forces at the feet. And oh, hang on, I think my lights are about to go out because I have not moved enough in my room. There we go. I think okay. And so, you know, so even the problem of building a simulator that will give you those contact forces is a challenging problem, right? Or impulses and so on, and getting ones which are numerically stable and so on. And so there's some fudging which goes on there, you know, assumptions that, and I don't know that they're unreasonable, but they're, you know, they're assumptions, a lot of assumptions all the way baked in. You know, if you're going to have Coulomb friction, that's an approximation for a bulk phenomenon and all these things. And so you show these arrows, you know, which are exactly the contact forces. And I wanted to ask sort of, first of all, is there any sensors on the feet? And the second one is, because how reliable are those? And in these sort of techniques where you're trying to learn without all of that complexity of, you know, complementarity or whatever it is that the technique is that they're using, how well is that likely to work? Can you just sort of reflect on your experience with simulation, because you're obviously using the simulator as a model in the MPC, right?
Okay, so let me answer the first question first. You know, do I have a contact sensor on the foot? No, we don't have any. So we don't have torque sensors and force sensors as well in our robot. We only have motors, and we measure the current, because the current of the motor is proportional to the torque of the motor. And if you have a large granulation force, then it can be felt at the motor if your transmission is transparent. If your gear ratio is low, if you have a small friction, if you have a small inertia in your gearbox, then it will transmit the granulation force to the motor very well. And then the motor can feel that by having the current. So we measure the current, and we use very traditional technique for fault detection or contact detection for manipulator, so-called momentum observer. So we use, I mean, the principle is very simple. Like, you have expected dynamics with your mass and inertia and Coriolis terms, and you measure the torque, and then you integrate that error, and then you measure that, you know, if you don't have any external torque, then you will have zero. If you have some external torque, then you have some spike. So that's how the momentum observer works. And then you use a momentum observer to detect the contact. And we use that to control the MPC and the state estimation as well, because we use leg kinematics, which is in contact, to have a more precise state estimation. So anyway, and your second question was, I forgot.
Well, Marcus, well, yeah, I didn't do a good job of asking very crisp questions. It was a bit rambly, but what I was kind of wondering is about sort of your experience with using sort of numerical models of those things. Yeah.
So okay, so we use simulation, like dynamic simulation package. Like, we are using RSS'21, developed by Jaemin Hwangbo at KAIST. He's my colleague, one of my colleagues. And we use that only when we validate our control design. For example, if we want to validate the robot, like walking on step and stairs, and then roughness on the train, we use that LiShim to validate our controller. But before that, in the design phase, we don't use any simulator. We use only MATLAB to integrate dynamics. So we have our own MATLAB script to integrate dynamics and then test our controller. And what I can say is it depends on how much the simulation matches well with the experiment. It depends on the situation. It depends on the types of motion you are executing. It depends on the ground, especially the ground stiffness is actually very different from the simulation and real experiment. So I mean, but generally, the motion that worked in simulation also in our robot, and we actually put a lot of effort to make the model of the robot matches well with the simulation model. For example, I think we have a friction compensation algorithm going on, and we have a really good, identified motor constant and inertia of the rotor, something like that, to match very well. Yeah, but I don't know. I think it depends on your preference, how much you trust or how much you rely on the model. But I do not rely on model very much, yeah, because of my experience. Yeah.
It seems to be my my observation is that the best roboticists don't. That's what makes them roboticists, right? It's interesting also if you talk to biologists as well. I've noticed that they have, they have an appreciation for the real thing, and I think their systems are so complex, I guess, that they are skeptical of any sort of very low order description. But you brought up something which I was wanting to ask you a lot about. Actually, it was the part which I got really, I think is really exciting. And you just touched on it now when you were talking about MATLAB and how you're using it, which is to talk about the design problem. So this thing where, so I do a little bit of work also where we use sort of optimization tools, and I'm interested in robot design problems. It's quite different. We think predominantly about sensors, which is quite different from designing a gear train, for example, so you gave this nice example of optimizing the gear ratios and then how you start, and then you might have to iterate, and but at least there's sort of an optimization. You have an optimization form, and then in the end you see the final result of the leg jumping up, which was great. Yeah. But then so I noticed you found this, you sort of let me see if I've got this right. It seemed like you parameterize the problem, you figure out what sort of the optimum gear ratio, you find it's 29.5 to 1 or something. I've forgotten exactly what it was, but it was some slightly strange number like that. And then you realize that using sort of in your design, you've got this planetary gear mechanism that does that. So I was sort of curious about doing the optimization sort of one level beyond. So figuring out not just sort of a parameterization of the gear ratios, but basically the actual gear mechanisms, right? So that's much, much harder, because now we're not talking about tweaking a few parameters subject to bounds or some things, but actually some sort of qualitative changes in the structure. Do you guys think about any of that, or do you have any thoughts on whether that's feasible or whether that would be useful? It seems like a hard computational problem, but it seems very interesting.
Okay, so I mean, to answer the question, I think first of all, I want to say that I'm not the researcher who mainly work on the gear itself. So my understanding of gear is actually not very deep. So some of the researchers, some Japanese researcher, I think he published some paper about the gear design, how to reduce the friction, and then how to design the shape of the teeth to reduce the frictions. And he had a really detailed model. And then my understanding is not that deep compared to that. So, but what I can say is, first of all, even though we chose 23.94 to 1 gear ratio, it's not possible, because gear teeth, number of gear teeth is integer, as you know. So we have to choose a very close gear ratio to that one found by optimization. And we know that this is not optimal anymore, but we know that this is probably good. And then I want to verify that by really making the hardware. And I mean, what I can say is it just provides some good number for initial fabrication. And I mean, so interestingly, I suggest to use 16:1 to my student as a gear ratio because I think that's heuristically good number for me. I don't have any good answer. Why 16:1? And then the student came up with the optimization, and then he said that 23:1 is better. And I don't know. I mean, 16:1 is better. 23:1 is better. But we saw that 23:1 is working well. And so, I mean, there's a lot of ambiguity in the design. And then in terms of the integer number of tests, we actually trying to use mixed integer nonlinear optimization to design the gears. And the big robot Hound is actually the gear ratio chosen by that optimization as well. So we are actually preparing some papers about that result. Yeah.
Oh, that's interesting. And the other thing which you just said earlier, which has kind of given me, because you were talking about this, the momentum observer, is that I was thinking that predominantly it's about driving the actuators, but there's more than that actually. You could, and I don't know if this is true, but it seems like you might have one optimum for driving the actuators and another optimum for observing the momentum. There could be another a different trade-off there, a different set of gears.
Actually, yeah, I mean, it's a trade-off because if you have a larger gear ratio, then you have a larger torque, but you have a larger friction and larger inertia, and then you don't feel very much. Yeah, so it's actually the trade-off. So I think it's important to. I think it's a very interesting aspect. Yeah.
Yeah. No, that's I got a lot out of your talk. So one of the things which really, I really like this thing where you see it running and then you say like, oh, actually this is 90 degrees. And I realized, oh yeah, those cables are floating like this. And then you spoke about sort of these magnetic, I shouldn't say it was running. I guess it was walking. It was a walking gait with 3 legs down, 1 leg moving. But still, I was not kind of expecting that. It was like a scene in the film. And so obviously there was a pretty sophisticated foot design there in order for you to connect and disconnect at the appropriate time, I guess.
Mm-hmm.
So just first of all, that's I mean, I've never seen anything at all like that. I mean, I have seen some climbing robots, I guess, but they, mainly they're talking about like hooks or gecko inspired, nano tubes or whatever for sticking to the surface. Never something like that, which I could imagine you could use for a ship hull or something. So what I didn't kind of get is why you guys studied that. Just out of curiosity, just to show it could be done? Or do you had an application in mind? Or I thought it was fascinating, which is good enough for me, but I'm just curious what your motivation was.
Yeah, I mean, my main motivation comes from the shipbuilding industry. Because they have to inspect the hull of the vessel outside and inside, and they have really, long and curved pipes inside of a factory and then ship. And then they are all made with steel and they are all magnetic. And then they don't have good tools or good, mobile robot for that kind of environment. I mean, for outside the surface, there is some company, I think company name is Gecko, I think, Gecko Robotics. They have a magnetic field and then they have some system. But I mean, the field system, I mean, we know the field system has some disadvantage in the mobility compared to the legged robot because they cannot go over discontinuous terrain, something like stepping stones, and then the ladders, something like that. So the same disadvantage happens in the vertical wall climbing robot because if you have a discontinuous terrain, if you have like obstacles, then this regular robot can overcome that, while the wheeled robot cannot overcome those kind of obstacles. And then if you just the ship, they have a really complex obstacle. I mean, especially inside of the ship. So yeah,
I can see that.
Mm.
Yeah, no, that makes sense. Thank you. That's excellent. So we're kind of at the end of our time here. And I just wanted to say again, thank you for making the time, and specifically also for doing the earlier time, which was a very painful time. And I will say that as I walked to my office this evening, I saw some squirrels, and every time I see squirrels, I'm going to think of your talk now. And that's most wonderful. So thank you very much. And I hope you're able to catch a little bit of the conference, and maybe we can bump into you in Gathertown, or someone else can, and I'm sure you'll get some extra questions there. So again, thanks so much, and congratulations on being selected by the selection committee for an early career spotlight talk. So I appreciate your time. Thanks a lot.
Thank you very much.
Bye.
Bye.